Hi, good day. My name is Hassan Ali Mujhtaba, and today I want to show you how a nanoscale solution can solve one of biotechnology's biggest problems. What if one of the biggest obstacles in biotechnology happens at a scale so small we can't see it, but so important we can't ignore it? In biotechnology, producing therapeutic proteins isn't the hard part. Folding them correctly is. In E. coli, many complex proteins misfold and collapse into inactive inclusion bodies long before they ever become medicine. Therapeutic proteins must fold into precise three-dimensional shapes to function, but when we express disulfide-rich proteins in E. coli, they frequently misfold, clump together, and lose all biological activity. This misfolding is one of the biggest bottlenecks in biologic production. Strain engineering, redox optimization, and co-expressing chaperones help. But misfolding still persists. Nanoparticles have recently emerged as promising artificial chaperones, but we still lack clear comparative data. So our research asked a simple but important question. Can gold or silica nanoparticles improve folding efficiency, solubility, and activity of a disulfide-rich protein expressed in E. coli? We designed a controlled refolding experiment using four identical conditions: no additive, the natural chaperones GroEL/GroES, silica nanoparticles, and gold nanoparticles. The protein was expressed in E. coli, inclusion bodies were isolated, fully denatured in urea, and then refolded under each condition. We measured soluble recovery, enzymatic activity, total yield, aggregation using DLS, and secondary structure through circular dichroism, all performed in triplicate. The results were remarkably clear. Gold nanoparticles outperformed every other condition. They produced 56% soluble recovery, about 72% native-like activity, and a 37 milligram per liter yield, the highest across all tests. While silica nanoparticles and GroEL/GroES improved folding, gold nanoparticles consistently delivered the best solubility, lowest aggregation, and strongest activity. In short, gold nanoparticles didn't just help the protein fold, they helped it fold correctly. So why did gold work so well? Gold nanoparticles provide a stabilizing surface that supports partially folded proteins. They prevent early misfolding, reduce aggregation, and act like a temporary scaffold while the protein searches for its correct shape. This makes gold nanoparticles a scalable and cost-effective strategy for increasing yields of therapeutically important proteins, a meaningful advancement for biopharmaceutical manufacturing. Our study shows that eco-engineered gold nanoparticles act as highly effective artificial chaperones for refolding disulfide-rich proteins in E. coli. They improved solubility, activity, and structural integrity, outperforming both silica nanoparticles and natural chaperones. By enabling proteins to fold properly, gold nanoparticles may help make biologic medicines more efficient, more accessible, and ultimately more affordable. Thank you for attention.